For this lesson, we're going to talk about Fourier integrals and transforms. The Fourier integral may be thought of as a continuous contour part of the Fourier series where the limit L approaches infinity. Suppose f of x is defined for all real x with the assumption that this integral converges absolutely. Then the Fourier integral representation of f of x is given by 1 over pi, integral from 0 to infinity. So a omega cosine omega x plus b omega sine omega x e omega, where a omega is evaluated, okay, by, or a of omega is obtained by evaluating this improper integral. This is your b omega. Okay, so let us represent the given function f of x as a Fourier integral. So f of x 2 from negative 2 to 2 and then 0 otherwise. So we integrate from negative infinity to positive infinity here. But take note that it is 0 otherwise or beyond or outside of the interval negative 2 to 2. So we just integrate from negative 2 to 2. Your f of t is 2. And then multiplied by cosine omega t dt. So omega will be taken as a constant. We integrate with respect to t. Okay, so the integral will be 4 over omega sine 2 omega. So this will be your a, which is a function of omega. And for the coefficient b, okay, so integral from negative 2 to 2. So this time 2 and multiply by sine omega t. And the integral will be equal to 0. Okay. Then the Fourier integral representation of f of x will be given as follows. So this is okay. So this is equal to 0. Okay, so everything here will be 0. So we just integrate from 0 to positive infinity your a omega multiplied by cosine omega. So this is your Fourier integral representation of your f of x. And let's talk about the Fourier transform. The Fourier transform of f of t is a complex Fourier integral representation of f of t. So if f of t is piecewise continuous on the closed interval negative L to L, okay, with the assumption that this integral converges absolutely, then the Fourier transform of the function f of t will be defined as follows. So this is the operator, the Fourier transform operator. You're given the function f of t. Now, this, if you have omega here, this means that this is a function of omega. And that is equal to 1 over square root of 2 pi from negative infinity to positive infinity. F of t multiplied by e to the negative I omega t dt. So the resulting function, as you can see, will contain a complex variable. And the Fourier transform of f of t, as you can see, is a function in terms of the new variable omega. The Fourier transform of f of t is a function, you may use Fourier transforms table of some basic functions on page 536 from Advanced Engineering Mathematics 10th edition by Crazy. The inverse Fourier transform f of omega denoted by this symbol is the function defined as follows. So this is the inverse operator symbol, okay, and the resulting function has to be a function of t, and then this is the given function in terms of omega, and the inverse is 1 over square root of 2 pi from negative infinity to positive infinity f of omega e to the negative I omega t d omega for all t provided that the above integral will converge. Okay, let A be a positive constant. Find the Fourier transform of f of t, which is a product of the unit step function. If you recall, this is the graph of the unit step function. Another name for the unit step function is the Heaviside. Okay, so this is the graph. Your u is 1 from for t greater than 0 or equal to 0, and then for t less than 0, your u is equal to 0. Okay. So when you simplify, okay, so your k is equal to 0, this is the unit step function. If you multiply by e to the negative 80, we get the following. So e to the negative 80 for t greater than or equal to 0, and then 0 for t less than 0. So the Fourier transform of u of t times e to the negative 80, this is just t, is equal to 1 over square root of 2 pi from negative infinity to infinity f of t e to the negative I omega t dt. Okay, so we substitute from 0 to infinity. So we just consider only t greater than or equal to 0 because your f of t is 0 for t less than 0. So we just integrate from 0 to positive infinity. Okay, I forgot here to, okay, so I should, okay, so there should be 1 over, okay, 1 over square root of 2 pi here, okay, 0 to infinity. Your f of t is e to the negative 80, e to the negative I omega t dt. You can combine the powers of e here, so you can rewrite it as negative of the quantity a plus I omega t. So this will be treated as a constant. So integral of e to the u is e to the u, so you have a correction factor of 1 over a plus I omega. But take note that when t approaches infinity, this will be equal to 0. So, and then when t is equal to 0, then this one is equal to 1. And what is left here will be 1 over square root of 2 pi and the negative of the negative 1 over alpha plus I omega. So this will be your Fourier transform. So this conforms with the one in the Fourier transform table from Kreyszig. Okay, from the Fourier transform table, okay, you will have the Fourier transform of e to the negative 80 squared as equal to this quantity. Okay, or the Fourier transform of e to the negative 80 squared is equal to square root of pi over a multiplied by e to the negative omega squared over 4a. So what is the Fourier transform of e to the pi t squared? What is the inverse Fourier transform of e raised to negative 4 omega squared? So we're going to use this formula, okay, from the transform table. So for the first question, okay, if you have e to the negative, this is the standard form e to the negative at squared, then your a should be equal to negative pi. And the Fourier transform of e to the pi t squared, where a is negative pi, okay, will be equal to square root of pi over a. A is negative pi. E to the negative omega squared over 4 times negative pi. Okay? And then simplifying, you get I times e to the omega squared over 4i. Because square root, why is it I? Square root of negative 1, this will cancel out. No? Square root of negative 1 is I. And for the inverse transform, okay, e to the negative omega squared over 4a, we equate that to e to the negative 4 omega squared, okay, then 4 is equal to 1 over 4a, giving you a equals 16. Okay, so when you get the inverse transform of this, okay, that will be square root of a over pi. You get the reciprocal for the correction factor. Okay, but a here is 16, and then you have pi here, and then the function has to be e to the negative at squared. So a is 16, so you have e negative 16t squared. Okay, so this is your inverse transform. Now we go to an example of the application of the Fourier series in heat conduction problem. Okay, so the general solution of one-dimensional heat conduction equation for a slender bar whose ends are maintained at 0 degree is given as follows. Okay, so this is the general solution. Okay, so when t is equal to 0, okay, that is the initial value problem, so t is equal to 0. Now, this exponential function contains t here, so everything will be 0, e to the 0 is 1. So giving you only b sub n multiplied by sine n pi x over L. Okay, so your b sub n, of course, will be evaluated using this integral, no? From the Fourier series expansion. Okay, so solve the heat conduction problem. This is partial derivative, second order partial derivative with respect to x. And then this is the partial derivative of u with respect to the variable t. So x is defined from 0 to 5. T here denotes time, no? So time must be greater than 0. So subjected to the following initial conditions. No? So u of 0t is 0, u of 5t is equal to 0, and u of x0 is equal to x. Okay, so the standard equation for heat conduction problem is omega squared uxx equals ut, and therefore you will take omega squared to be 8. And then the period is equal to, so L here is equal to 5, so the period is equal to 10. And then this is your general solution. Okay, this is your omega squared, no? So we substitute Okay, your omega squared, and then this is L squared, so 5 squared. So n pi x over L, or n pi x over 5. And then evaluating b sub n will give you 2 over 5, 2 over L from 0 to L. X is your f of x. So take note that in the initial condition, or the particular solution for u of x0 is equal to f of x. Okay, so since this is given, so you have x here, so sine n pi x over 5. So integrate by parts, okay, will give you the coefficient negative 10 over n pi cosine n pi, or negative 1 raised to n plus 1, 10 over n pi for your b sub n. And then this one we substitute here in the general solution. Okay, or to get the particular solution. So therefore, okay, so this is your b sub n, but you can factor out 10 over pi. So negative 1 raised to n plus 1 over n. Okay, so e to the negative n squared pi squared t over 25 sine n pi x over n. Okay, so this is the particular solution of the heat conduction problem.